In the previous video, we looked at what is absolute uncertainty, fractional percentage uncertainty, as well as the identities, the four groups of identities that we use to combine uncertainties together. Number 1, plus or minus. Number 2, what happens if things are multiplied or divided together. Number 3, what if there are powers involved in your equation. And number 4, what if there are constant multipliers or dividers involved. But these are if an equation is given to you. We look at one example for that. But what if there is no equation given to you? Then how would you solve? That is what this example video is about. It's a deep dive. Let's go and see the first one. Here we have a thermometer question where they tell us that a thermometer can be read to an accuracy of plus minus 0.5 Celsius. Where did they get this? How did they even know this uncertainty? Well, for thermometers specifically, when you look at thermometers, standard ones, the smallest division is typically 1 degree Celsius. But each time you look at a reading, let's say I'm going to take a measurement here, I put my eye there, every time your eye look, the uncertainty will be plus minus half the smallest division. So I say half the smallest division, which is going to be 0.5 Celsius. Okay, so that's where we get the uncertainty of 0.5 for thermometer. And pretty much any scale, every time you look one time, you read one time, that's going to be half a smallest division. But anyway, here you are measuring a temperature rise from 40 to 100. What is the percentage uncertainty in the measurement of this temperature rise? Ooh, we need to draw a thermometer. Okay, let's make some thermometers here. I'm going to draw a vertical line. Oops. And another one here. Oi, what happened to my drawing? Oh, I want to use a shape. Oh, sorry. Ah, this is the line. Okay. Not very straight, but never mind. We have at one measurement 40 Celsius. So here is like 40. Then it increase until 100. So in between there are many markings, but I'm not going to draw all the markings. So how's the uncertainty going to work? When you are reading a change in temperature, the first reading you are looking is actually at 40. So when you look at the 40, you make first reading. That's going to have an uncertainty of plus minus 0.5 Celsius. Then the temperature increase, reach 100. Okay, then you look again. You put your eye there. There's another uncertainty there, plus minus 0.5 Celsius. So your eye look 2 times, means got double uncertainty lor. So if you want to find, at the end of the day, what's the percentage uncertainty, we got to say, all right, this is a temperature rise. So it's like a change in temperature. So if I say, all right, change in temperature is going to be, let's take final minus initial. So we have, this is our equation, minus 100 minus 40. This will give us 60 Celsius change in temperature, going from low to high. This is our delta theta. How about the uncertainty? Now look very carefully. This is when we have 2 uncertainties. Each of these theta have its own uncertainty and we are minusing. So we want to combine uncertainty. Combine absolute uncertainty, which will be each time you read is 0.5. You read again is 0.5. So total uncertainty in the change in angle is going to be 1 Celsius, plus minus. So we can say, oh, change in uncertainty, that's change in angle, change in uncertainty. Change in angle will be 60 Celsius plus minus 1 degree. But we want to find the percentage, right? So we have to find percentage uncertainty in theta. That will be 1 Celsius over 60. Oh, times 100. Forgot times 100. This one will give us 1 over 60 times 100%. 1.666666667% is going to be best answer D for this question. Key things to remember is, when your eye look one time, you have half smallest division. Depends on the instrument roughly, but for rulers, lengths, when we measure, actually we look 2 times. One time you look, uncertainty. You look again, another uncertainty. Alright, let's look at the next one. Another one for another instrument. This one also no equation, but we have to put together the uncertainty. Here you have 4 identical rods. The rods are these things here lah. The rods are placed side by side and their total width is measured with vernier calipers. The measurement that you read on the vernier calipers is 8.4, but then you also have 0 reading. You look 2 times. You look at 0 and you look again when you are at the full measurement. So 2 times. What is the width of one rod? In this length that we just measured, this is the 4 widths because there are 4 stuck together, right? So this is 4W. Maybe let's start by finding the value first. So if 4 of these widths are 8.4 mm, then one width is going to be 8.4 divided by 4. That will give us 2.1. So each single one of these is 2.1 millimeter. How about the uncertainty? This is where you have some problem here. You see, when you check 0 reading on the calipers, your eye look at the scale 1 time. That's why you already have an uncertainty. Then when you read at 8.4, your eye look at the scale again. 2 times you look. So uncertainty again. So you want to combine the uncertainty. Combine uncertainty. How do we combine? Got equation meh? Usually, what we do is we take 8.4, right? You see on the left side, 8.4. We usually minus the 0 reading. This is there's no 0 reading, so we just minus 0 lor. But this is a case where the uncertainties will add together. So we add uncertainty. So the uncertainty in 4 of W, which is what we just read, will be 0.1 plus 0.1. And all this is in millimeter. So 0.1 plus 0.1. 0.2 millimeter for the whole reading of 8.4, including 0 error. But wait, this is for 4 of the width. So if you want to find 1, so the uncertainty in 1 reading is multiplied by 4. So we have to divide by 4. Chop up into 4. This now, divide by 4, will give us 0.05 millimeter. That is your uncertainty. And now we can write out the final answer. So when you're writing the final answer, the first step you want to do is make sure you round off to 1 SF. So 1 SF, 0.05 looks good. Okay, we'll keep 1 SF. So plus minus 0.05, keep your unit. Then your value must follow the same decimal place. So if this is 2 decimal place, that means your answer should also have 2.10. Follow 2 decimal place. So based on this, we should get a value of closest value is B. So the answer that we can choose for this uncertainty is B. So it's pretty neat that although each reading we take by vernier caliper as uncertainty, if you stack many together like this, you can divide by the number of stacking that we have. This is what I call multiple measurements, and you divide the uncertainty by that multiple. Which is also why if I ask you a challenge question, hey, you got paper at home, right? Find the thickness of 1 paper. Wow, very hard. Paper is very thin, you know. But what you could do is you stack many paper. It's like a book, almost A4 paper. Then you measure this width. This height or thickness. Then you divide by 100 sheets of paper. So if I say, oh, I have uncertainty in T, I can divide it by 100 because I have 100 sheets. So that's why we stack multiples to reduce the uncertainty in a single value. Now to finish off this video, let's go back to the notes and look at this last example question. If you have not tried this, I encourage you to pause the video, try it out first. Just take a pen, doodle some stuff, see how far you can get. And then you come back and we look at the 2 methods to do this thing. So go ahead, pause and try it out. Alright, so here we have, it's adapted question from a MCQ question. A student wished to determine the density of lead. Lead is pretty heavy. What she does is she measures the mass and diameter of a small sphere lead. It's tiny little metal ball. She measures mass, diameter. Okay, what are we supposed to do? Calculate A, density, percentage uncertainty, and the absolute uncertainty of density. Oh, we need to find the equation. Okay. Here is a case where they never give you equation. So what you need to do is you need to create your own equation. So maybe I will say, okay, how density got equation? God, there's only one I know. Density equals to mass over volume. But volume of a sphere? Oh, volume of a sphere. Gotta remember the maths a bit. Volume of a sphere is 4/3 pi r cubed. Of course, you can convert that in terms of diameter, but I'm just writing the general one. So if you put these two together, what you have is a density equation, which is m over 3/4 pi r cubed. There, we have created our own equation to find the uncertainty and also the value of density. So I'm going to go ahead and plug in the value for density first. Where should we write it? No space already. We squeeze it here because later on a save space for the uncertainty part. So this one, if you plug in your values, 3/4. Mass is 0.506, but you must convert it to kg. So 10⁻3. Divide by pi radius. Let's use the radius 1.1. I'm going to write here radius 1.10 in millimeter. We'll leave the uncertainty soon. So this is 1.1 times 10 to the -3. Don't forget the cube. Ugh, so squashed there. This value, if you plug in everything, we should get a pretty big value actually. Very high density. 90757 kilogram per meter cube. Okay, that's the first part. So we got density. Great. Now the uncertainties. This is where it gets fun. Percentage uncertainty of density. How are we going to find that? There are a few methods. The first method is to use the identity that we have learned in the previous video. So you will look at the density equation that is written on the top left. So this. Who contribute uncertainty? Mass and diameter, which is also radius. So actually, we can create an equation such as the percentage uncertainty in a density equals to percentage uncertainty in mass plus 3 radius, right? Radius square. So 3 times of the percentage uncertainty in the radius. That's how we can find this. So we can say, all right, we can plug these together. Percentage uncertainty in the mass is going to be, how to find 0.005 over 0.506 times 100. Yeah, put bracket lah. Okay, put bracket. Plus 3 times of percentage uncertainty in radius. Ooh, how do we find that? If you look back at what we wrote just now, radius is divided by half, right? Radius is d over 2. Hey, that's like a multiple measurement. Multiple radius make up a diameter. Radius plus radius. This whole thing is diameter. So you can also divide the uncertainty by 2. 0.01. But actually, if you double check the percentage uncertainty, they are the same. So it doesn't matter which one you take. You can take radius, okay lah, 0.01 divided by 1.10 times 100. You would get an uncertainty in radius. By the way, I'm going to do a quick check. Is it the same? Can we divide like that? Okay. So radius, your uncertainty will be 0.9%. If you want to check for diameter, you take 0.02 divided by 2.20 times 100. That's your percentage uncertainty in diameter. That will be also the same. It should be the same lah. So this will be 0.9 also. So it doesn't matter which one you take. You just take either one, the percentage is the same. So this is 0.9%. This is also 0.9%. But although their uncertainty percentage is the same, their absolute uncertainty is different. So know this fact. This is our identity from the equation. R equals to D divided by a constant 2. Percentage unchanged. But the absolute uncertainty gets divided and split smaller. Alright, anyway, let's continue our calculation down here. What do we get down here? Add together the uncertainty, percentage. we should get roughly a value of 3.7%. What does this mean? It means 3.7% of your value is the absolute uncertainty. This is what it really means. So the next part is they ask you to find absolute uncertainty. So you need to multiply by absolute uncertainty. Okay, let's do it here on the right side maybe. No, let's do it at the bottom. So 3.7% of our value is error. Wow, so big. Okay. So to find our absolute uncertainty now, we say 3.7 divided by 100. This amount is the error. So what's our value just now? Our value of density is all the way up here, 90757. So we're going to put 90757 inside there. And what do you get for the final value? So we get about 3358 kilograms per meter negative 3. Oh, that's pretty big. How do we report the final value? Seems a bit strange. Our value of density just now from the previous part, we got 90757, right? So when you want to write the final answer, let's write it on the right side. Therefore, final answer reported, we will say density here equals to, remember the formula or the format? First step, uncertainty must be 1 SF only. So you look on the left side, I already underline where is my 1 SF. So I'm going to write the uncertainty first. This will be plus minus 3000. I round it off lah. Then your value must follow the placing of your uncertainty. So what placing is this? This placing is what we call the 1000 placing. Because it's 3000. I don't care the 100 and the 10 and the digit don't have. So I look at my P, I'm a row, sorry not P, on the down here. I look at the 1000 placing, which is my 0 here. So I need to round it off at that point. So my answer I'm going to write is 91000. Rounded off also to the 1000 placing. So after that, it's all 0000. Rounded already ma. Don't forget to write your unit, kilogram per meter cube. Of course, this one may look a bit weird to you. You're like, miss, all the 0 looks a bit weird. So another method, or the preferred method, is actually to write this in standard form. Standard form means I will write it 9.1. So one number and then a dot. Plus minus. This will become how many? 1, 2, 3, 4. So 1, 2, 3, 4. This is 0.3 times 10 to the 3 kg per meter cube. I like this. This is called standard form. Nice. Hashtag standard form. So here is where you put the prefix. Alright. That's how you can find one method with using the identities, which is the one that we use right here. You can also use fractional uncertainty. That is totally fine as well. You would write it a little bit different though. You would say the uncertainty in row over row equals to uncertainty in M over M plus 3 times the uncertainty in R over R, or diameter. Same value lah. Okay, another method that we may use is what we call half the range method, which is right down there at the bottom. What does it mean to half the range? How do we half the range for this? Only got one value, one equation. So if you want to find uncertainty with half the range, you need to do a lot more calculations here, because the equation goes like this. To find the uncertainty in your density, you need to figure out what is the maximum value of density minus the smallest possible value of density. And then you minus and you divide by half. Wow, this method also can, but you need to do a lot of calculation. So in case you ever forget the uncertainty identity, you may do this. It is generally not recommended for theory papers, but it's definitely much more common in paper 3 and paper 5, which are all lab practical papers. So let's work through it and see. All right, what happens if you cannot and you panic, you forgot the identity? Okay, so maximum value of density. What's the equation again? I keep forgetting. Density equals to 3 over 4, right? M times pi r cubed. Okay. Let's find the maximum. So rho max will be 3 over 4 times mass. Okay, what's the maximum mass we can have? We need to look back at this thing. If you look at this crowded area, this one, the maximum is 0.506 plus 0.005. Because plus minus one, maximum will be plus. So let's write 0.506. 0.506 plus the uncertainty, 0.005. That's the maximum mass. Then we continue on. Pi times radius. What's the maximum radius? You go here and see 1.1 plus 0.01. 1.1 plus 0.01. Okay, lor. Write it out. 1.1 plus 0.01. Don't forget the cube. We should get a value here of... Oh, I forgot to include the prefix. Yeah. Okay, let's include prefix. 10 to the negative 3 because that's in grams. We convert to kg. And the radius also have to convert, right? It's in what? Millimeter. Aiyo. Okay, we have to include millimeter. So times 10 to the negative 3 but cube. Did we do the millimeter just now? We did include it, right? Up here. Yeah, we did. 10 negative 3 cube. Okay, now it's correct. So now with this prefix, we should get 89199. Now if you got this, you will notice that something is a bit suspicious. If you look at the top left, our value of density is 90757. How is the maximum value less than the actual value? So you scratch your head and you're like, wait, means just now we used this value here. This is our maximum mass, right? Which is correct if you want to use the maximum value. But for radius, actually you want to use the smallest radius. So now, oh, radius used wrong now. Okay, we drop off the radius and try again. Okay, down the bottom, we need to put instead the minimum r. So this will be 1.1 like just now, but minus 0.01. Now this one, what do we get? So 942 is what the calculator gives me, 94200. So do reality check a bit. Okay, my average value is 90757. This is higher, right? Okay, good, very good, higher. Okay, so to summarize what is happening here, we are taking to find the maximum value equals to, we need to use 3 over 4, the mass that is maximum, divide by pi times the radius that is minimum cube, and that only will give you your largest value of rho, because you must divide by the smallest number, right? Okay, let's do the rest. So we do another same thing again, but now we want to find the minimum. This will be equal to 3 over 4. We repeat the same thing, but now we put the minimum value on top. So minimum will be 0.506 minus the uncertainty, 0.005 times 10 to the negative 3. Pi times the radius maximum. So you do 1.10 plus 0.01 plus the uncertainty lah. So this will be cube. Don't forget the prefix, 10 negative 3, but also must cube this one. What do we get for this? My calculator says 87454. Is it smaller than the actual value? Yes, it is. So to summarize, this one is using the equation where you have rho min equals to 3 over 4. The mass, this time you use minimum because they're proportional. Pi times r maximum. If you divide by a very large number, your value will become very small. So that is going to be the equation that we're using. Okay, finally we can use our equation. The uncertainty here will be half the maximum value, 94200, minus the minimum value, 87454. And what do we get? 3373. And that is our uncertainty. Wow, after so long. Okay. So our reported value, therefore, the reported value of density is going to be, if we round off to 1000 again, this will be 91000 plus 91000, oh correct, plus 3000 kilogram per meter cube. Is that the same as our previous answer? Let's check. On the right side, 91000, 3000, same lah, okay lah. So this method can seem very long, especially you need to use maximum, minimum, but it is what we call a foolproof, kind of, almost foolproof way if you do not remember the identities. So what I would recommend is, for theory, make sure you know your identity. This one here, very important. For paper 3 or paper 5, if you don't remember identities at that time and you don't know what to do, go back to your half the range method. So half of the range, which is the maximum minus minimum. Okay, so that's all for this section on uncertainties. Next up, I'll see you in the section on vectors, where we do some triangles and forces. That's all for this video. I'll see you in the next one.